Hello everybody, welcome back. We're going to find some more volumes today, but as promised we are going to find volumes of solids that have holes in them. So this problem is just a little tweak on the last problem we did in the last video. In the last video we did the volume of the solid that is formed when you just take the cosine from 0 to pi over 4. Take that whole area, it's like a curvy trapezoidal area, and revolve it. Okay. Now what we're doing is we're introducing this kind of upper boundary, lower boundary situation like we had in areas, where sometimes it was just the area under a curve, but sometimes it was the area between two curves, right? There's an upper and there's a lower boundary, and that's what we have here. So what we want is we want to take this area between cosine and sine, and we want to revolve that around the x-axis. So to get the picture of that solid, I'm going to do the same thing I've done before. I'm going to do a reflection. So when I reflect sine, it's going to look something like that. And then when I reflect cosine, let's see if I can do this right. Something like that. Well, I made it curve back a little bit, but you get the drift. Okay, so I have this area down here. And then I'm going to do my trick here of putting circles on the ends. Okay, so this is an interesting solid here. I said that the last one looked like a dog bowl. I really think this one looks like a dog bowl. If you don't have a dog, or you never have, you may notice if you've seen them, sometimes the bowls look like this. They're like, I guess it's so the dog doesn't knock it over. They're smaller on the top and they're wider on the bottom. And that's what this looks like to me, that kind of shape, right? But also, I say that it looks like a bowl because it actually has this part where you could put water, right? Because there's this hollow part. So this part that's colored in, that's solid, right? Because that's where the area was. And so that's when I revolved it, that created, you know, a solid mass. This empty space here, though, this empty space between the sine curve and the x-axis, when this area revolved, nothing got swept out there. So in my solid, that remains empty space. And so what that creates is the bowl part of my dog bowl, right? So in this solid, if you think of it as a bowl like this part is solid, ceramic, whatever you want to say, and then there's an actual bowl cut out in the middle. Right. So let's take a look at the visual creations of this that I made. There it's from the side, right? Again, from the side it doesn't really look, or from the front I guess, it doesn't really look like much. But if we turn it, we can see this bowl type of image, right? So when we look at it kind of from the top, you can see the pink is the outside, and then the empty space is swirled like green. So it's when I graph this, I graph the cosine in pink and I graph the sine in green. So where the sine swept out, you can see it created this kind of cone-like shape. Where the cosine swept out, it created this pink. So the space between the pink and the green is solid. Inside the green is empty. You can also look at it kind of from the bottom, from that side. And from that side, again, you have to kind of imagine this is solid, because if it was actually solid in the picture, it would just look like a big pink blob, right? But this is what we see here, is how that, you're looking at it from the bottom, and you can sort of see through it here, how it comes down to a point, right? You can see it here. It comes down to a point. It's happening here as well. So this comes to a point. Now, the very last layer at the bottom here is going to be all pink, right? Because they come together right there. Okay. But let's think about what these slices are going to look like. If I come in here and I draw a rectangle, and remember, we always want to create from the axis of rotation to the outer part of our shape. Okay. So if I go from here to here and I do a revolution, I'm going to get a cylinder, right? I'm going to get a cylinder with my outer curve, with my cosine. Right? That's going to be my, that's what would happen if you just revolved cosine, which we know. Right? The problem is we also have that empty space in the middle, and that empty space is from here. Right? So in other words, I don't exactly get a disc here. I get more like what we call a washer. If you've ever seen a washer, like in World, the little thing that goes with the bolt, right? So what I have here is an outer radius that when you revolve it creates a cylinder. And then you have an inner radius that comes up to the bottom function that is going to create and dictate where your empty space goes. So if I'm looking at this slice, if I lay it down and look at it like this, I've got my cylinder, but my cylinder has a hole in it. So if I want to find the volume of this cylinder, that's not too hard. I just have to do a little subtraction, right? I'm going to do pi, and I call it your major or your outer radius squared times the height, and then subtract out this middle, right? So if this middle, this empty space, we'll say that, use a different color here. The radius of that I'm going to call lowercase r. All I have to do is subtract out that space. So if I take the whole cylinder and subtract this empty space out, I'm left with just this part. In other words, just this shaded red part, because I don't want to include the area or the volume. If there's a space where there's empty space, we're not including that area, then when you swoop it around the axis, there's going to be a hole in your solid, and we have to account for that. Okay, now it's not as hard as you would think it is. It's still a solid of revolution. Okay? So all we're going to do is we're going to create an equation for the volume of one of these slices, accounting for the fact that it's going to have a hole in it. And in fact, that's what we just did here. Right? Every single one of these slices is going to be the volume of the whole big cylinder, the outer one, take away the volume of the hole, the volume of the empty space in the middle. So the only thing that, when there's a hole in here, the only real layer that this adds is distinguishing between the radius that created the outside of the shape and the radius that created the hole or the inside of the shape. And when you do that, I want you to just think about the upper versus lower boundaries. It's pretty much what we're doing here. Your upper boundary is going to be the outside of the shape, and your inner boundary is going to be the inside of the shape. So when they revolve, your inner boundary will be what dictates where your empty space is. Between there and there is going to be where your solid space is. Okay. So this is our definition every single time. We want to take the whole big cylinder that was dictated by the outer radius and subtract the little cylinder that was dictated, or subtract the empty space that's dictated by the inner radius. Okay. Okay, so let's take a look at this method. This method is called the washer method. Again, like I said before, it's a cylinder with a piece taken out. And so I wanted to show you these pictures that might help you understand why we do what we do in the washer method. Anytime there's empty space between the area you're revolving and your axis of rotation, you're going to have a hole in your disc. Okay, so if you look at this picture here, if I have this purple area, this little leaf shape here, if I'm going around the y-axis as they show in this picture, we've got empty space between our purple area and the y-axis. So I know for a fact that when I revolve, I'm going to have a hole in my shape. If you think about it, when you draw your rectangles, outer versus inner or upper versus lower, when that gets revolved, as you can see here, it's revolving, but there's space in here. That's going to leave a hole in your disc. Okay. Same thing down here. This area doesn't come all the way down to the x-axis. So when I create my disc, when I revolve this, that's fine. It still creates a cool disc, but it also leaves this empty space or this hole in the middle. And when that happens, we use our washer method. So in these pictures, when you're doing a washer, you always want to identify what was the radius on the outside, your outer radius, and also what was your radius on the inside, your inner radius. And your formula is going to be the same every time. It's going to be pi times your outer radius squared times height minus pi times your inner radius squared times height. Now look what that's going to turn into. We know the height, that's going to be our dx, right? So I'm going to have pi r squared minus pi little r squared, all of that times dx. Now, if you want to, you can rewrite that as pi big R squared minus little r squared, and even pull the pi out of the integral, get it out of the way. And that's fine. But what you better not do, and I feel like I shouldn't have to say this, but people do it all the time. Again, we get to doing calculus and we forget everything we ever knew. People do this all the time. They say, oh, it's a washer, big R minus little r, and square it. This is not the same thing as this. This has to be FOILed, and if you FOIL it, you get this. And that is not what this is. Do not do that. You cannot just subtract them and then square. Order of operations. I need pi r squared minus pi little r squared. If you want to factor out the pi, have at it. But it has to be big R squared minus little r squared. Outer radius squared minus inner radius squared every single time. All right, so let's revisit this cosine and sine problem. Let's see if we can write an integral using washers for this volume. So again, the first thing that I'm going to do is I'm going to do this reflection, and I'm going to color code it a little bit here to try to help us out. So reflect my sine. In blue, and we'll reflect our cosine in red. It's kind of a terrible drawing, my apologies. But so I have all of this area and all of this. That's kind of what it would look if you sliced it in half. And then when I put the circles on the end, we can see what we have, right? We have that dog bowl. Right. Over here, what I want to draw is a couple of the slices. So again, it's more important to be able to picture the slice than it is to be able to picture the whole thing. So what I want you to see is the difference in what the slices are going to look like as you move left to right down this shape. Down here towards 0, the bottom, if you will, or the leftmost side of the shape, we're going to have these discs, right? And the hole in the disc is going to be pretty small, right? Because down near 0, the cosine, or I'm sorry, the sine isn't very far from the axis, right? So I'm going to have these big discs that are following cosine, and the holes in the middle are going to be pretty small. Right. As I move out, though, if I go maybe out here, I'm still going to have a pretty big disc. But now notice my hole's a lot bigger. Look how big that hole is. So the slices out in there, they might have holes like that. If I come all the way out here, like towards the end here, I'm still going to have a fairly big slice, but now almost the whole thing is whole. So in other words, if you did a slice like right in here, this, look how little solid space you have versus how big the hole is. Right? So your shapes towards the end there going to look more like this. But what I want you to see is that even though the way the slices look is changing, there's some things that are staying consistent. That outer shell, the outer edge of each slice, is always, always, always dictated by the same function. It's always the cosine that's determining where the outer edge of my cylinder is. The inner edge, this one here, is always, always, always being determined by the sine, right? When the sine is low, we have a little hole. As the sine grows and grows and grows, the holes inside of our shapes get bigger and bigger and bigger. So what I have here, if I look at that picture real quick, is I figured out my outer radius, what's determining the outside, and my inner radius, what's determining the inside. Once I've done that, as soon as you recognize that you have washers, identify your outer radius, identify your inner radius, it's a real quick jump to writing the integral. So all we got to do two things here. We got to use our formula, and then we have to figure out what our limits of integration are going to be. Okay, so I'm going to write the equation for one of the cylinders generically, integrate to add them all up. So I need pi outer radius squared, so cosine squared, minus pi times little radius squared, so sine x squared. Okay. And then dx is my height. So again, all this is pi r squared h. We're just really stretching it here, right? Pi radius squared times height. The dx is the height. Okay. So again, if I want to, I can bring the pi out and write this as cosine squared x minus sine squared x. That's fine. We just have to figure out our limits of integration. Okay, so notice they didn't give us any here. They don't need to, because just like the ones in the last chapter with, or the last section with enclosed areas, right? I'm starting at 0 and I'm ending at this point right here where the area ends, where they touch. And we know where that is. That's at pi over 4, right? We're looking for the place where cosine x and sine x are equal to each other, and that has to happen at pi over 4. So I know I'm integrating from 0 to pi over 4. Okay. So again, anytime there is space between the area that you're revolving and the axis, anytime this space exists, we know we're going to have to do a washer method. Okay. So let's do one more together. Okay, we want to write the integral for the volume of the solid generated when the region below is revolved around the line y equals -1. Okay, so this is a good one because it's revolving around something other than the x-axis, which is a good thing for us to try. So the first thing that I'm going to do is put the line y equals -1 in there. Okay. The next thing I'm going to do is identify what these functions are. Right? They didn't give it to us, but they're just lines, so we should be able to figure it out. Right. This looks like it has a slope of 1/2, so this looks like it's y equals 1/2 x. It's starting at 0. And the blue one looks like it has a slope of 1, so it looks like this one is just y equals x, no? Yep, pretty nice. Okay, so if I want to revolve that area that's labeled there around the axis, not around the axis, around the line y equals 1, then I need to reflect this area, not over the x-axis, over the line y equals 1. So I'm literally going to just reflect these points for the blue line. My blue line. Oh, it would be okay. Okay, and then I'm going to do the same thing for my red line. So there'll be one there. So we have this same area down here, and then we'll put our circles on the ends to picture the area, the volume. I see like a cheerleader's megaphone here. So if you're looking at just a slice, let's say we came in right here. Whoops. Let's say I came in right here and drew a slice. Okay, you'll notice this part's going to be solid, but you're also going to have a hole in the middle there. Right? If I come up here and draw a slice, you can see the solid part will be bigger, but so will the hole. Right? All of this space in here, empty space in the plane, becomes a hole in the shape. So we know we have a hole in the shape. All we have to do is figure out what's my outer radius and what is my inner radius. So when I look at these shapes, when I go from my axis of rotation out to my outer edge here, that's the line y equals x, but let's be careful here. X is the distance between the x-axis and this graph, but I'm not going around x, I'm going around the line y equals -1. So if you break this down a little bit, let me get color here. Okay, from here to here, that is 1, right? The distance between -1 and the axis is 1, and then I still have to keep going from here up to the line, and that distance is x. So my outer radius here isn't just x, it's x down to the axis plus 1 more to get to the line x is negative or y is -1. So my outer radius is x plus 1 more. Okay, let's do the same thing for my inner radius. When I come over here and I try to figure out, okay, from my axis of rotation to the inside, in other words, to where the empty space ends and where the solid begins, that's going to be my inner radius. Now, I know, once again, this distance here is 1, right? The distance between my line, my axis of rotation, and the x-axis, that's 1. But I need to add that to this distance that goes from the axis up to the curve. Well, great news. Whoops, it's my inner radius, right? This distance, I know, this distance has to be 1/2 x plus 1 more. So 1/2 x plus 1 more. Okay. So notice again, if we were going around the x-axis, the only thing that would change is that these plus 1s wouldn't be there. But like I said in the beginning of yesterday's video, I don't ever want you to assume that your radius is just simply determined by the function. If you're going around something other than the axis, you're going to have to adjust those. So always remember that the radius is the distance between your axis of rotation and your curve. Okay. So now that I have these two radiuses, I can very easily write my integral. Okay. They put this vertical line here at 8, so I know I'm stopping at 8. So from 0 to 8, I'm going to put my pi out front. So I need larger radius squared, so outer radius squared, minus my inner radius squared, times the height dx. Done. Okay. Please put any questions that came up for you on washers or anything that's still lingering about discs, and we will discuss anything that came up for you tomorrow. Have a wonderful day.